This tutorial provides an introduction to digitalization and data acquisition systems for the digitization of the measurement signals, within the framework of the European project titled Personalized Education in Measurement Science and Technology Empowered by Machine Learning. The modern measurement approach relies on the digitalization of the measurand. This means that the output of each of the new sensors must be an electrical quantity. It can be a voltage, a current, an impedance, etc. The sensor's output is still a physical analog signal, which should be read by a converter whose input must be a voltage. For this reason, between the PC and the sensors, a signal conditioning stage, which converts any electrical quantity to a voltage, should be put. The process of converting the analog voltage, coming from the signal conditioning stage to a digital quantity on the bus of a PC, is done by the data acquisition board, the DAC, which is the object of this tutorial. The process of converting the analog voltage, coming from the signal conditioning stage to a digital quantity on the bus of a PC, is done by the data acquisition board, the DAC, which is the object of this tutorial. Before going into the structure of a data acquisition system, let us start with some remarks on how a signal can be digitized, namely how the analog to digital conversion is performed. The input of a data acquisition board is an analog voltage, so a signal defined in continuous domains both in time and in amplitude. The process of digitization implies the discretization of the signal in both domains. In fact, we can observe the signal in certain time instants and report it with a finite number of digits. The first process, namely the discretization in the time domain, is called sampling. The second one, namely the report with a finite number of digits, is called quantization. So the basic structure of the analog to digital converter is the following. The input signal V is discretized in the time domain through a circuit called a sample and hold, which will be shown in the following. The sample, held by the sample and hold circuitry, is then resolved in a grid, namely its value is checked against the possible voltage levels. The output is a logic digital signal. The different structures of an ADC are not the topic of this tutorial. If you are interested, you can find other materials online. To correctly configure a data acquisition board, it is necessary to sample our time domain signal correctly. A correct sampling means that, under certain conditions, the input signal can be reconstructed from its samples without loss of information. Let us hypothesize that the signal we want to sample has a limited bandwidth, namely that its Fourier transform is 0 over a certain frequency. If this is not valid, let us assume to add to the signal a low-pass filter, which is usually inserted at the input of instruments. An ideal sampling is obtained by multiplying the input signal by a comb of Dirac deltas, each spaced by a certain time step, called from now on sampling time, Ts. Of course, a real sampling requires a certain amount of time to retrieve the value of the input, so the Dirac delta becomes a rectangular with a width, depending on the speed of the sample and hold. Here, the sampling is down. It can be demonstrated, applying the discrete time Fourier transform to the samples, that the spectrum of the sampled signal is periodic in the frequency domain, with a periodicity given by the sampling frequency Fs. In other words, the spectrum of the sampled signal adds infinite replicas of the spectrum of the continuous time signal, each distanced of a value that is equal to f dash. Since we are interested in the initial time domain signal, we have to ensure that we are not mixing its spectrum, or, in other words, those replicas due to the limited sampling frequency do not overlap with each other. So we have to ensure that the distance Fs is higher than the bandwidth of the input signal, which corresponds to 2 times Fmax. It is well known that the Fourier transform of the signal is Hermitian, so it is defined in plus or minus Fmax, and its negative part is the complex conjugate of the positive one. So, with these considerations, it is easy to deduct the sampling theorem, or Shannon's theorem, which states that, given a time domain signal upper limited to a maximum frequency Fmax, it can be correctly reconstructed from its samples if the sampling frequency Fs is at least 2 times higher than Fmax. If this does not happen, our spectrum is affected by aliasing, namely, the overlap of the replicas. Here you can see what happens when we sample a time domain signal. At first, we have the Fourier transform of the signal. It is symmetric and limited to Fmax. When we sample and we apply the discrete time Fourier transform, we get the spectrum S tilde, periodic in the frequency domain, with a periodicity of FSS. Then we want to reconstruct the original signal from S tilde. We can digitally extract all the components up to half FSS, and then compute the anti-transformation. The frequency Fs divided by 2 is also called the Nyquist frequency. When the Shannon condition is not met, the different replicas partly overlap one over the other, and their output is indistinguishable. This condition is called aliasing, and the part of the spectrum affected by it will not be retrieved in any way. In real working conditions, the process of sampling is far from being ideal. In particular, it is worth reminding that the observation interval cannot be infinite, so we cannot observe really slow dynamics. In fact, the observation interval limits the frequency resolution. The sampling cannot be instantaneous, and the clock can be affected by small deviations, called jitter. The sample and hold introduce a small distortion in the required samples. The low-pass filter cannot be ideal. In practical applications, one should use a sampling frequency that provides coherent sampling, so that the number of samples per period of each component is an integer, and as high as possible to avoid possible non-idealities. In fact, the Shannon theorem gives a lower bound on the sampling frequency. Here, the sample and hold circuit is shown. It basically consists of a switch that closes the input voltage that has to be measured on a capacitor, which has to be fastly charged and slowly discharged, to be sure that in the second part of the sampling, the hold part, the voltage across the capacitor is kept constant. Nowadays, the circuit is also composed of an operational amplifier, which can ensure the high impedance of the input and a lower time constant. After having reminded the basics of sampling, we can go into the details of the structure of a dot acquisition board. Here you can see the block diagram of a data acquisition board. Any data acquisition board can have one or multiple of the following: analog inputs, channels devoted to the measurement of the analog signals. Analog outputs. The board can also have a digital-to-analog converter called DAC, which can provide a voltage signal made by the digital samples sent to the DAC from the PC. It has to be highlighted that the DAC is not a signal generator, namely, the output power of the DAC is low. Digital Y/0. Some pins can be devoted to digital signals, logic values that can be high or low. The channels are reconfigurable since they are employed as 3 state inputs. Trigger and timing pins. They can be used for analog and/or digital synchronization. The analog inputs are then connected to the single DAC or ADC with a multiplexer. This means that there is a serial scan of the active channels that will then be sampled by the ADC. After the multiplexer, an instrumentation amplifier sets the gain of the channel to be matched with the ADC range, providing also a high impedance, higher than 1 megaohm, to the input. Similarly to the inputs, the analog outputs are also connected to the DAC, digital to analog converter, through a multiplexer. Again, this is necessary due to the single ADC in the DAQ. Finally, digital data is stored in a FIFO, first in, first out, register, or taken if we consider the outputs, and then sent to the bus to the RAM or the PC for storage. The analog input can be connected to the DAC either in single-ended mode on the left of the slide or in differential configuration. In the first case, only the positive polarity of the channel is connected, while the ground reference is given by the DAC itself. This kind of connection saves one input terminal and can double the number of signals connected, equal to the total number of pins, but on the other side, it suffers from a higher noise level and no rejection of the common mode noise. It is useful when no particular requirements of noise rejection are asked, or there are no strict accuracy specifications, for example, the temperature measurement for the control of the temperature in a house. The second connection is the differential connection mode. In this case, the input of the instrumentation amplifier is connected to 2 different pins, hence it measures the difference between the positive and the negative poles of the sensors. In this case, the noise introduced by common mode fluctuation is completely rejected, and the noise circulating in the ground of the DAC is not added to the measurement. So the differential connection is used when the measurements are required to be more accurate, or when the configuration of the sensor imposes a differential measurement, such as for thermocouples or the output of measurement bridges. The typical number of channels that can be found on a data acquisition board can go from 8 to more than 80. The ADC in the DAQ that performs the digitization of the signal has maximum sampling frequency, depending also on the specific architecture of the ABC itself. In general, a single ADC is responsible for the measurements of all the channels, and so the sampling frequency of the single channels also depends on the number of active channels. So if 3 channels are connected, to get a second sample, the first channel has to wait for the other 2 to be sampled. In other words, the channel's sampling frequency is equal to the ADC sampling frequency divided by the number of channels. It also has to take into account that the sampling frequency can be set only to a certain integer downsample of the maximum sampling frequency. The ADC frequency and its divider valves are reported on the datasheet and vary between DAQs. The typical ADC frequencies go from hundreds of hertz to megahertz. The ADC cannot measure any voltage value, but the one who tolls inside its dynamics, which is typically from -5 to +5 volts. To change the range of measurement to higher or lower values, the instrumentation amplifier in the DAC can set different fixed gains. To exploit the range in the most useful way, the range must be set higher than the range of the input signal, but as near as possible to the maximum values, both for positive and negative values. Here you can find some examples of typical gains that can be set for the instrumentation amplifier, as well as the relative range of the channels. For a gain equal to 100, the range is set to plus or minus 50 millivolts, so the input signal should be lower than 50 millivolts. The gain should be chosen as close as possible to the input dynamics to increase the resolution of the digital signal, namely, to decrease the quantization error. In fact, the DAK is characterized by a specific number of bits of resolution, which, together with the range, defines the quantization error as delta 5 equal to the range of the channel divided by 2 to the power of n. The lower the range, the higher the resolution. Typical resolutions are of the order of 12 to 18 bits. Given the noise floor of the DAC, it makes no sense to increase its number, except for highly accurate applications. In fact, it has to be remembered that the total uncertainty of the DAC itself is not only given by the resolution, but also by the noise of the electronic part, the offset and gain errors, the linearity of the sample and hold, and so forth. To summarize, when choosing a DAC device for your measurement setup, you have to take care of these aspects. Choose a DAC with several channels higher than the number of signals that have to be measured. Choose a DAC with a sampling frequency that satisfies the Shannon theorem so that the channel sampling frequency is higher than 2 times the maximum frequency of the signal, or that satisfies other limits in the project, a specific number of samples per period. Choose a DAQ that can satisfy the requirements of the measurement range, so that its range is higher than the maximum expected input amplitude. Choose a resolution according to the expected quantization error. Choose a DAR whose noise is lower than the accuracy you want to have of the signal digitized. Of course they are there. Take care of the cost of the DAQ. Slide 22. Thank you for following this. In the tutorial, you can find more information about the project on the website and the LinkedIn page. If you have any questions or need further information, you can write to the following email address. Thank you for your attention. This video was produced through the collaboration of SS Cyril and Methodius University of Skopje, the University of Niš and Politecnico di Milano, within the framework of the European project Personalized Education in Measurement Science and Technology Empowered by Machine Learning. More information about the project can be found on the project website and LinkedIn page.